Hello, my name is Trevor Plant and I'm a coach for the Institute of Physics. And with me I have Joe.
Hello, my name's Joanna Kent, and I work with Trevor, also as a coach for the Institute of Physics.
This is the first of our energy videos and is aimed at all teachers who teach energy as part of physics, roughly in the age range of 11 to 14. There are two other videos which you might like to watch after this one. What Joe and I are going to do is just to have a little conversation about the approach to teaching energy that uses energy stores and some of the reasons for this and some of the implications of it. Joe, do you want to start by asking me a question?
I'd love to, Trevor. Um, so let's start off by thinking, can you explain what is an energy store and why is using energy stores a useful idea?
That is a good question and one that a lot of teachers ask us. The point about energy is just energy. It doesn't change what it is, which was one of the features of the old way of teaching energy. We use the idea of stores to describe how that energy can be calculated. When we're first introducing the idea of energy stores, obviously with the younger children, they won't be doing any calculations, but we are laying the groundwork for calculations later on. So if we say energy is in a gravity store or a gravitational store, or energy is in a kinetic store, then later on, what we hope the students will be able to do is to recognize the store which has changed, either been emptied or filled, and be able to do a calculation based on that. But to know which calculation to do, you have to know which energy store has been filled or emptied. Think of it as a little bit like a container. The most important thing about the container is how much does it hold. So that's what we're doing, is we're trying to lay the groundwork for doing calculations of how much has the energy in that store changed. Perhaps you could tell us, Joe, which stores are there?
Well, yeah, which stores there are would really depend on which age group of students we're talking about. But as we're considering students between the ages of 11 and 14, the stores that are generally considered at this age are a kinetic store, gravitational store, elastic store, chemical store, and a thermal store. There are other stores that are introduced once the children get into the older age groups, but I think we'll leave those for now. So that being said, lots of teachers will have taught electrical, sound, and light as forms of energy. Why aren't these stores?
Well, basically, because it's not possible to do a calculation of the number of joules that would have changed in going from one situation or one moment in time to another. We can't, for example, freeze frame a sound wave and talk about how many joules of energy are in that sound wave. If you know something about the ways that we measure sound, for example, you've probably heard of the unit of the decibel. And if you look up the definition of decibel, or maybe you already know it, but it's not related to a number of joules, it's related to how many joules per second. Now that's a very important unit called the watt, and what that tells us is the rate at which energy is being transferred, usually from one store to another store. So again, if we go back to the idea of having containers, the important property of a container is how much it can hold. But in looking at things like sound, what we're doing is we are moving the liquid from one container to another. So it's how many per second are we pouring from one container to another. And it's the same thing in looking at energy. What's important in sound and those other quantities that you measure is how many joules per second are being transferred. So for those things, it's not like there's a static store of energy. We are moving energy from one to another, in which case the important question is not how many joules, but how many joules per second are being transferred. And electricity is like that. If we multiply the voltage times the current, then we have a power calculation. And the answer is how many joules per second of work being done, electrical work being done by that circuit. Perhaps you could give us some examples, Joe, of how do we know which stores are emptying and which stores are filling?
That is a very good question, because it's very easy to get into quite a complicated sequence of energy shifting from one store to another. So the way we deal with that is by using what we call a start point and an end point. So say, for example, we've got a ball, and if the ball is held up, we can say that there is gravitational store, and then if I let it go, it'll drop. What happens to the energy in the gravitational store is that it will be shifted into a kinetic store as the ball moves. So our start point would be when the ball's held up, and we need to identify an end point, because we could go on and on and on. You know, the ball hits the ground, it rolls along the floor, and so on. So for the end point, I would choose the point at which the ball is just about to hit the floor, so that all the energy in the gravitational store has been transferred to the kinetic store when the ball is moving at its fastest. Obviously, without doing calculations, this just becomes a story, which is something that I will look at in one of the videos that are part of this sequence later on. So we need to identify this start and end point, and that is the key thing to talking about energy shifting from one store to another. So I've talked about shifting. How do we choose the start and end points?
That is a good question. And the important thing to notice is that we always will have a choice about where we put these. I'll say more about this in the second video of this series. So the example I'm going to use is this toy mouse that I'm just going to show you a very, very brief video of. And we pull the mouse back. There is some mechanism inside, and then the mouse goes forward like that. So what would be good start and end points to use here? Well, as I say, there is always a choice, and some teachers I talk to would probably have their start point as now, and then they would want to talk about chemical store decreasing and link that to the fact that we are able to do work in pulling the mouse backwards. So we pull the mouse backwards like that. Now, an alternative would be to have your start point at the point where you have already pulled the mouse back. The second case, you stand some sort of chance of eventually being able to do a calculation. It would be quite a difficult calculation to do, but nonetheless, you could in principle try and do some sort of calculation as to the energy stored in an elastic store, because inside the workings of this, there is some rubber band or spring or something like that, which gets stretched. And again, there's a choice about where we put the endpoint. If we run the video again, we can see that, as I said before, pull the mouse back, it moves forward. Now, lots of teachers would choose that point there where it's finished and it's at the end of its motion. But again, if we say, well, which energy store has increased in value, has been filled in that case, well, the mouse has stopped dead, so the carpet presumably and the mouse itself must be slightly warmer, so we have a thermal store which has increased. Again, your chance of being able to measure that and therefore do any calculation is very, very slim. If instead you put the endpoint as when the mouse is going at its fastest, then you can measure the speed that it's traveling at. And so here again, you've got a reasonable chance of being able to do a calculation. So the answer to your question, Joe, is not simple, I'm afraid, and it's one that I will explore in more detail in the second video in this series. There is no right or wrong answer. It depends what it is you're trying to get over. So if you want to be able to do a calculation, you need to think carefully about which start and end point might be possible and might make it easier for you to be able to do some sort of meaningful calculation. But there's nothing wrong with choosing other start and end points if it's to illustrate a point about different energy stores. So I hope that helps in kind of just highlighting that there is an issue around choosing your start and end points. But the question I need to ask Joe now is what's wrong with transform? I think we've been very careful in this video to not use the word transform, which when we were teachers, we would probably have used quite a lot. We're saying that transform is not a good word to use when we're talking about energy shifting from one store to another. Can you explain, Joe, what exactly is wrong with the word transform and why we try and avoid that word?
Yes, I'll have a go, Trevor. When we say transform, that implies something, sort of like a spell, like a Harry Potter spell, that you're going to change something from one thing to another. But of course, energy is just energy, and it's always energy. All that happens is it's stored in different places, which we call the energy stores. So the different stores give us a way of doing calculations so that we can look at, as you've already said, so that we can look at how much energy has shifted from one store to another, but it is still energy. There's no transforming taking place at all. So it's a misleading word that I think it's good to avoid. You might have noticed that we've said shifting. So shall we have a look at some examples of choosing start and endpoints and identifying the stores? Right, let's start by having a look at a pendulum as an example of energy shifting from one store to another. So here I have a teddy hanging on a string, having great fun, swinging from side to side. Just let you observe that for a moment or two, and you can see that he's swinging quite freely. And then I'm going to pause him so that I can talk about the energy shifting from one store to another and identifying start and end points. So I am going to choose as a start point the point at which he is at the highest point of his swing. So at this point, he's raised in the Earth's gravitational field. So energy in the gravitational store, when he's at the highest point of his swing, will be at its maximum. So there's energy in the gravitational store. Then when we let him go, he moves. So there's energy in his kinetic store. So we can't get energy from nowhere. The law of conservation of energy that says that from the gravitational store, the energy has now shifted into the kinetic store. Of course, on the swing, he then goes up the other side of the swing. That's what swinging is. You go backwards and forwards. So he's raised up again. The energy that was in the kinetic store is now shifted to the gravitational store again. So we've got this continual shifting of energy, gravitational store, kinetic store, gravitational store, which does bring out one point with a pendulum that at the point where he changes direction, of course, he's momentarily stationary, so there's no energy in the kinetic store. It's all in the gravitational store. That's one example. We could continue with that and we could do calculations. Have you got another example, Trevor?
Well, I'm just going to show quite a simple example that a lot of teachers ask me about, the idea of a torch. So if we shine a torch for a while and then switch it off, what would we say about that? And the thing to notice is if I define my start point, for example, as say now, and then I could wait for a long time or not, because that would make it quite a dull video, wouldn't it? So I'll take my end point as now, then what's changed in the meantime? Well, this is a battery powered torch. So what has happened is the battery is a little bit flatter. As we said earlier, this is a chemical process. So the store which is decreased is a chemical store. But the interesting thing that teachers who've been teaching for a number of years kind of need to make this jump. What's changed in the room from my start point and my end point has nothing to do with light, has it? The room is a little bit warmer because the light fell on the objects around the room, and that caused them to warm up slightly. The battery and the wires in the torch conducted electric current, and therefore they'll be slightly warmer. So again, the whole environment is ever so slightly warmer. So in terms of energy store that is increased, it's a thermal store. Now, this goes back to what we said earlier, that knowing what store is emptied and what store is filled is not necessarily a guide to what the device is for. I'll pick up that point in the second video in the series. So in fact, the torch is the same as the candle in that if we just look at the energy stores, the story between the start point and the end point, if we have a lit candle, then again, from our start point to our end point, the decrease is going to be in a chemical store and the increase is going to be in a thermal store, both the same in terms of the energy analysis. In terms of how they work, quite different, and that's where the interesting physics comes, is by analyzing exactly what is going on in how the device is working. The energy story tells us nothing about that. That's a different area of physics entirely. So that concludes the first of these 3 videos in this section. I hope you found it interesting, and I really hope you're going to watch the other 2 videos as well. Thank you very much.
Thank you. Goodbye.
Goodbye.